Hello, in this video we're going to talk about empirical formulas. And so as an illustration of what this is, we have to start with percent composition. And so this is something we talked about in chapter 2, where if you take the mass of one element in a compound and divide by the total mass of the compound, multiply it by 100, you get what's called the mass percent. And so an example down here, what is the mass percent of hydrogen in ammonia? Well, you take the mass of the hydrogen, there's 3 of them in ammonia, divide it by the total mass of ammonia, multiply it by 100 to get a percent, and then you get the mass percent of hydrogen in ammonia. Okay, well what if we want to go the other way? What if we have a mass percent and we want to convert it to a formula? So this is something that we do experimentally. There are a couple different ways in chemistry where you can determine the elemental composition of a sample, of what percent of the mass of a sample is this element, what percent of your sample is that element. You can find that experimentally, and then, well, you want to go from that experimental mass percentage to a formula. And so if you do this, you convert the mass percent to a formula, you get what's called the empirical formula. And so this gives you the simplest whole number ratio of the atoms. So say, for instance, you had hydrogen peroxide, H2O2, the empirical formula is going to be HO. Because if you think of it, the mass percentage of hydrogen in HO is the same as the mass percent of hydrogen in H2O2. And so we can't really tell those apart when you're going from the mass percent to the formula. So what you can do is just find the empirical formula, and then in a second step, if you know the molar mass of the sample, then you can find what the molecular formula is. Another example on here is the active ingredient in catnip, C10H4O2, which is this molecule here in the middle. Its empirical formula is the simplest whole number ratio of the atoms involved. So if you divide everything by 2, you get this on the right, and that's your empirical formula. And while we're talking about catnip, my sister's cat, Cleo, she likes catnip. Yeah. Okay, so how do we do this? How do we go from mass percentages to the chemical formula? So there's a process here, and ultimately, if you get the right answer and show some valid mathematical steps, I'm fine however you do it. But it's good to teach a process, and so here's the process that I teach. So, alright, from the experiment, you'll get the percent by mass of each element, and so that's in this box up here. And then, well, the first thing you want to do is find how many grams of each element you have if you assume some sample size. And when you have a percentage, well, it's really easy to assume a sample size of 100. And so if you assume 100 grams of your total sample, then that means if you have 30% of one element, well, you have 30 grams of that element. And so that's this step here. And this works because the elemental composition, the mass percentages and all that is irrespective of the size of the sample. So you can assume whatever size of sample you want. We're just going to pick 100 grams because it makes the math easier. Ultimately, you take the percent and you drop the percent and you replace it with a G and you move on, is what you wind up doing. But this is the reason why. Alright, so once you have the number of grams of each element, the next step is to convert that into the number of moles of each element. You want to know the relative amount on a mole basis, and if you just divide each element, the mass of it, by its molar mass, then you get the number of moles of each element, just like we've done before. So now you have the number of moles of each element. If you divide all of these by the smallest number of moles, you'll get the ratios of elements. And then now, sometimes you have to do some work to change all the subscripts to be integer values. And once you do that, then you have the empirical formula. So overall, the plan here is you assume a sample size, and then you convert from grams to moles, and then you figure out what the ratios are on a mole basis between your different elements in your sample, and then you get that into integer numbers, which is your empirical formula. So this needs an example. What's the empirical formula of a compound that's 40% carbon, 6.71% hydrogen, 53.3% oxygen? All of these percentages are by mass. Well, go back to your process. So the first thing we're going to do is turn the percentages into a mass by assuming we have a 100-gram sample. So the mathematical way to do this is you take your percentage, turn it into a decimal form, and then multiply it by 100 grams, and then you get 40 grams of carbon. You do the same thing with the hydrogen, the same thing with the oxygen. Ultimately, you take the percent sign, drop it, replace it with grams. But you want to know why you're doing that, right? So this is the reason why you do that. Okay, now we need to convert to moles. So if you take each of these masses from the first part and divide by the molar mass of that element, then you get moles. And so these are the moles of each element we have from our assumed sample size. And we're interested in the relative ratios between these. You can probably by now look at these and say, I've got a 1 to 2 to 1 ratio between carbon, hydrogen, and oxygen. And sometimes it's simple enough you can just see it. Other times you need to do a little bit of work and to be able to find out what that is. So let's show how you would do this work. Is you find the smallest number of moles you have. In this case it's 3.33 from the carbon and the oxygen. And if you divide all of these by the same 3.33, then you'll get 1 to 2 to 1. 1 mole of carbon for every 2 moles of hydrogen for every 1 mole of oxygen, irrespective of the sample size. Now, sometimes you have to work to change these to integer subscripts. In this case you don't. So then you just write down the empirical formula, CH2O. Ta-da! Here it is. This is the empirical formula of this compound. And if that's all that the question is asking, now you're finished. Oftentimes we ask a little more. So here's an example of a part B. What can we do if we want to continue this problem? Is we say, well, what if we know the molecular weight of this compound? We say that's 60 grams per mole. Then what's the molecular formula? So our empirical formula, if you calculate the molar mass of this, it's 30 grams per mole. Well, there's a pretty simple ratio between 30 grams per mole and 60 grams per mole. So if you multiply each of these subscripts by 2, which then the molar mass is multiplied by 2, you'll get a compound, C2H4O2, that has the molecular formula, and the molar mass matches what we found experimentally. And so this could be a molecule like acetic acid, for example. Now this matches kind of the process in real life because, all right, elemental analysis can give you the mass percentages, but mass spectrometry can give you the molecular weights. And so if you do both of these common analysis steps, then you can figure out what your molecular formula is by following this kind of process. So it's something that we do in chemistry. All right, another example. So what if your compound is 91.24% carbon and 8.75% hydrogen by mass, and you have a molar mass here? All right, what do? Well, the first thing you do is convert these to grams, and then you'll convert both of these to moles. So divide each of them by the molar mass of the respective element. So the top one we're dividing by carbon's molar mass, the bottom one by hydrogen's molar mass. And if you look at these answers, it's not very clear what the mole ratio is between the two. So in the next step, divide each of these by the smallest number of moles, and you'll get a 1 to 1.14 ratio. We need to do some work in order to convert these to integer ratios. So probably the simplest way to do this is just guess and check. What if I multiply it by 2? Nope. What if I multiply it by 3? Nope. Hey, what if I multiply it by 7? And then you get something that's very close to 8. 7.98. And then that's okay to round it to 8. So there's some limits here though, right? Why don't you round 1.14 down to 1 and this is just a 1-to-1 ratio? Well, you don't. So ultimately the limits of how much you can round here depend on the experimental precision of your method, which you don't know because you're just being given a problem. So I usually say if it's within a couple percent, feel free to round it. So in this case, 7.98 is within a percent or two of 8. So feel free to make that kind of rounding step. but I wouldn't do anything bigger than that. So don't round 1.14 to 1. That's a little bigger of a change. So if it's within 0.02, 0.03 of the integer, call that close enough. And I won't give you a problem that really pushes the limits beyond that. Alright, so again, we found the empirical formula of this compound. But now that we know the molecular mass, we can figure out the molecular formula of this compound, which is actually the real one. So first we calculate the molar mass of the empirical formula, which is 92 grams per mole. And then, again, I think it's easiest to just guess and check to find how many times you need to multiply the molar mass by to get the known mass of the whole compound. You can also make a ratio if this is easy enough for you. You can take the molar mass number here, and you can divide it by the molar mass of the empirical formula. So you have the molar mass of the known molecular formula, whatever that is, and the molar mass of the empirical formula. And if you just divide them by each other, you get 3. So now you take the molecular formula and you can multiply each of the subscripts by 3, and you get C21H24 as your molecular formula. And now you've answered the question. Do keep in mind that this is one of the very few times where we will take the subscripts in a molecular formula and multiply them by this factor. Normally if you're multiplying your compound by a number 3, well then that 3 just becomes a coefficient in front and you don't touch the subscripts. But in the case of molecular formulas, this is something we can do because we're still trying to figure out what these subscripts really are, so that's okay for us to do here. Alright, the last little bit in this chapter is a little nuance on this, determining the atomic mass with empirical formulas. And so this is kind of an interesting use case here. So say you had an empirical formula of some metal oxide, and you know the empirical formula is MO, a 1-to-1 ratio. You don't know the identity of the metal. This is different than our previous examples where we knew the identity of all the elements, we just didn't know the empirical formula. Here it's the other way around. The empirical formula is MO, we just don't know what the metal is. Now, say you take some of this metal and burn it in oxygen, and then you'll make a metal oxide. So you don't know what the metal is, but if you take it before it's MO and burn it and make the metal oxide with a 1-to-1 ratio in the empirical formula, now you have some new mass. Okay, so then how do we use this to figure out what element we have by finding the atomic mass of the metal? Maybe pause it and try to give it a try, and then we'll start again. Alright, so here's the trick. So if you take the mass of the metal oxide that's in the problem, and you subtract it from the mass of the metal that you started with, you know that you added 0.323 grams of oxygen. Because the metal oxide is just metal and oxygen, and if you start with just the metal and you know the mass of that, well, you can take the difference of the mass of metal oxide to find how much is just oxygen. Now, you can either turn these masses into mass percents, or you can just straight away go ahead and convert these to moles. So the mass of oxygen in this oxide is 0.323, and then you can find the moles of oxygen by dividing by the molar mass of oxygen. And, well, since the empirical formula is 1 metal for every 1 oxygen, this means that there's the same number of moles of metal in this sample, because it's a 1-to-1 mole ratio. Well, the problem tells you the mass of that sample, 0.490 grams, and then you figured out that it was 0.0202 moles of that metal. So if you take grams divided by moles, you'll get a molar mass. And then this molar mass matches magnesium, which is one of the elements that would make sense for it to make a 1-to-1 empirical formula with oxygen. So this is just kind of problem solving using these concepts in a much different way, and I do appreciate your textbook for taking the time to point this out. And that's what we have for now on empirical formulas. So give this some practice and we'll do a worksheet on it in class and carry on. Thank you for watching.